So today I would like to put the focus, after this very inspiring presentation of Wouter, to yet another topic. I believe it's more a mission I have to do in order to talk about healthy buildings in terms of energy efficiency. The term of a healthy building is mainly associated with the indoor environment in terms of the topics ergonomics, behavior, technology, as listed here with topics like air quality, room acoustics, lighting, occupant behavior, environmental psychology, as we just have heard, physical responses, and to some extent also technology. Now we all know that energy efficiency and indoor climate are strongly interconnected. And I think it's also quite obvious, and by the way, subject to a very promising new Annex project under the umbrella of the International Energy Agency, the Annex 66, where a lot of colleagues here are participating, that occupant behavior has a strong impact on the energy consumption. So I think it's obvious that variations in some of these listed measures here, like variations in the room temperature or in the air change rate here, the second part, or the hot water, the domestic hot water consumption, may result in a different picture of the primary energy demand. But the picture is even worse if you consider a combination of all of these things that might end up in a factor of 4 of difference in the respective performance indicator, here the primary energy demand. A second issue, also quite clear to you as a community, is that something that has to do with productivity. We have a lot of presentations at this conference dealing with that issue. But we all know that typical constraints and typical complaints in office buildings have mainly to do with the dissatisfaction of the thermal environment. So other complaints like bad indoor air quality, cold draft, etc., have a much less significance. And I think it's you who knows best to explain why this is obviously the case. Interesting to see is if we take a look at the life cycle cost of a building, and if in addition to the typical construction cost, maintenance cost, we take in addition into account the salaries, the staff salaries of the people actively working in these buildings, which is the red part of this cake here. So I think it's also clear that a healthy and comfortable environment has something to do with cognitive performance, which is to some extent also of ecological relevance. Last but not least, third example, the car industry currently asks us building physicists to develop new local thermal comfort models, as there is a severe problem associated with electromobility. Perhaps you know that. Installing a conventional heating system to an electric drive is a fairly bad idea, as you would bisect its range. So this is why the car industry asks us to develop new and to understand the process, to develop new energy-efficient climatization strategies, as range and cost is inherently connected with thermal comfort, as we also have investigated in a series of projects in Aachen recently. To summarize that, recreating healthy buildings has to do with comfort and ergonomics in terms of thermal comfort, indoor air quality, lighting, room acoustics. At the same time, we have to consider the just mentioned cognitive performance and health issues, all its mutual interdependencies, which are at the same time of economic relevance. But there's a third branch, it's the energy performance, and we have measures in order to influence the building here in terms of increasing the thermal quality performance of the building envelope, to integrate renewable energies, and also to efficiently operate our buildings. Now, buildings are constructed, as we all know, to provide a safe, healthy, and comfortable indoor environment where people can live and work together in a productive manner. But dear colleagues, I think it's clear that buildings are not primarily built to save energy. In this community, it's perfectly well understood how to build and operate an indoor environment in order to maximize or to optimize thermal comfort, health, etc. But I think healthy buildings of the future from an energy point of view are more than just perfectly insulated passive buildings. And when it comes to the transition from the traditional energy sources, fossil energy, to new renewable energies, it is important to see that the building sector can contribute a lot to that. Energy-related emissions contribute by more than 80% to the overall emissions. And it's simply the question if we are just consumers of a healthy environment or if we really want to build and operate healthy buildings in terms of energy efficiency. And in the following, I would like to summarize 5 key measures, which for me means recreating healthy buildings, and at the same time saying that this is a highly interdisciplinary task, which not a single institute, a single person can solve. Let us start with the very first part, the passive measures, clear to us all here. I think a very important issue is to increase the thermal quality performance of the building envelope. Now, thermal insulation is thereby a key element in order to minimize transmission losses through the building envelope. I think that's clear. And there exist several materials to do so. So for instance, for indoor surfaces, for indoor insulation, we know that surface active materials are a good idea, which make use of capillary action in order to transport moisture to the surface that the construction can dry out. Or for the exterior insulation, like shown on this picture, we have systems like, for instance, a thermal insulation composite system. But all such systems also have problems. So in this case, the problem with this type of system is that you physically decouple the thermal mass of the building with the external environment. And further, due to the reduced thermal capacity of that material, we observe that the dew point temperature of the external surface is undercut much more frequently than in a conventional construction. So obviously, the moisture on the building facade, and this is not an old facade, this is a just renovated building, shows us this characteristic algae growth. And I think it's clear, I wouldn't call that a healthy construction. But algae within facades are not necessarily a bad idea, as can be seen by this BIQ building here in Hamburg, for example. I think it's a very interesting project. Here a chloroplast is used, is filled into the gap into a transparent panel, and together with sun, carbon dioxide and nutrients, this facade is able to actively produce biomass and waste heat, and the resulting methane and heat is then used in order to contribute to the energy system of the building. So I think it's very important to always consider a right balance between thermal insulation and the HVAC systems of a building. Just putting insulation on a building, the outside or the inside, is not the only solution. It's a balance, the right balance between technology and insulation. And I think that's very important to keep in mind. Other issues here are air tightness and heat recovery that influence the energy performance. But let me consider another thing first. I think for me also the quality of workmanship is an important issue. So a typical renovation example is shown here. I took this picture from a study of Heike Böhmer from Hannover because I really liked that study. So subsidies are paid if a certain U value is achieved for a construction. And you know, for a certain U value, you need a certain insulation thickness. Of course, this insulation package can be squeezed into a much narrower space. Some pressure is required to do so. And now the result is, as no one will afterwards care, subsidies are paid, but this results in a very bad performance of the overall construction. So in this study of Heike Böhmer, it reveals that in 48% damages are due to faulty workmanship. And this clearly shows us that this is not a problem of the insulation material itself. It's more a problem of missing quality assurance. And this is, I think, another issue we really have to keep in mind. Okay, let me come up with this slide. Another issue is the passive use of solar energy. We all know what that is. So we can open the next part, the active measures. There exist several technologies in order to do so, like the active use of solar energy, for instance, with solar thermal systems, as indicated here. Other promising and important technologies are to make use of environmental energy. This can be achieved by shifting by shifting the energy to a different temperature level in order to make it usable in the building, and the heat pump process can be used in order to do that. And by talking about that, I think it's also interesting to see if you have a look at the energy types for space heating. So here I have shown the share of the renewable energies for space heating in Germany. It's a couple of years old, that slide, but I think it's clear to explain the problem here. So I'm talking about space heating, not the electricity production. And as you can see here, the share of renewables is around 5%. Now, the picture looks a bit different, as we can see that most of this fraction is contributed by solid biomass, and the so-called new renewable energies, namely geothermal energy, solar thermal energy, solar energy, etc., contribute by less than 1%. And so I think it's clear where we have to put some action on. Let me add two more issues here. Cogeneration of heat and power is another very important and promising technology. And last but not least, if we compare that to the thermophysiology of a human body, I must say a building is a very stupid thing because it can't maintain its core temperature with an accuracy of 0.1 degrees centigrade. Yeah, we have a huge variation, so perhaps think about that. Is load shifting in space and time in a building. Yeah, this is also a promising technology we can do. At this point, I would like to stress that the building sector offers the largest single potential for energy savings. The renewable energies currently contribute in Germany by around 90 terawatt hours a year to the electricity production, with around 110 to the heat production, and with around 80 to the passive solar energy in buildings. The interesting question is, what if we apply not the latest research, but state-of-the-art refurbishment renovation technology, as we have just talked about, to the existing building stock? And some colleagues estimated the potential of that. So a former colleague of mine, Gerd Hauser, once estimated that just these passive energy efficiency measures have an impact of around 700 terawatt hours. And my colleagues from RWTH Aachen University, Dirk Müller and Antonello Monti, estimated that the energy storage potential in buildings, by considering electrical and thermal storage in buildings, is, in a conservative estimation, at least 300 terawatt hours a year. Nice to see if you just compare currently the net energy electricity production from nuclear energy. And I think if you compare these numbers, it's very clear into which direction to go. Now, I have talked about Germany as a typical European country, and we all know that Europe has mainly a refurbishment problem. But that is clear. There are also other regions in the world which have yet different problems. So for instance, in India, and I thought this slide very inspiring, I borrowed that from an Indian colleague because I think it's a very excellent, it excellently shows the real problem here. If you consider that 70% of the building stock which will exist in the year 2030 have not yet even been built. So that shows us that we have here a huge responsibility and huge possibilities in terms of energy efficiency measures. Okay, let me add a third box here. It's control and optimization. Here we have emerging technologies like model predictive control, or the very important issue of commissioning and optimizing operation. Also an example here, a very interesting and challenging project. I don't want to say anything bad about that, so not to be misunderstood here. The Berlin Efficiency Plus building was designed as a net plus energy building. It has a very sophisticated energy system, and has a very advanced performance monitoring system installed here, providing evidence about the typical consumptions here, like domestic hot water, lighting, domestic power, space heating, and all the auxiliary energy, which is a bit higher here. Is a special energy concept and a showcase. That means it has a lot of IT installed here. Now, the problem is that in the very first operation phase of that building with the test family, and now you know perhaps what I want to tell you, with the test family, the family requested much higher indoor temperatures than were designed, and this resulted in a very bad energy performance in the end, because the heating system was operated at temperatures 15 to 20 Kelvin above its design temperature in order to meet these requested indoor air temperatures. So in the end, the heat pump coefficient of performance resulted in 2.3 instead of the estimated value of 3.5, which shows us that this has a very bad energy performance, which is not due to the technology. Here, the occupant behavior comes into the game. Yeah, and this is why I would like to add a last point here, a very important point for the future. It is fault detection and diagnosis. Another example, there exists a software in order to do that. It has been developed by colleagues from a university in Braunschweig, Brunswick, and Aachen. And this software Energy Navigator uses key performance indicators and operation rules as active functional descriptions. And from a computer science point of view, they are using finite state machines in order to model that. And this software allows you to compare the actual performance monitoring with the intended building operation in order to visualize bad energy performance or a mismatch between the states. So you can functionally describe the model. You have the whole HVAC system configuration with the active functional descriptions and operation evaluation, etc., which gives you a visual tool in order to evaluate the system and to detect faults. I think a very promising technology. Let me summarize that. Optimizing operation, healthy buildings of the future necessarily need to close the gap between commissioning and handover. They should be equipped with smart meters. They support operation optimization by fault detection systems, and they should be able to communicate these diagnostics to its users via smart devices. Okay, now to these three measures, I would like to add a fourth category, namely network compatibility. As I have told you before, due to the increased use of renewable energy sources, our buildings need to be able to store energy. This is a key element. Therefore, we need to develop decentralized energy storage systems. In order to make use of this energy, at the same time, we need to extend the boundaries, not only considering a single building, but to consider a city quarter or whatever our boundaries are. And another issue is that the control of a building energy system needs, with appropriate technology, for instance, demand-side management, to be connected to the superordinated control of a grid. And this is what demand management methods can do. In order to clarify the network compatibility issues, I have taken one picture here in order to just display the volatile nature of these renewable energy sources here for Germany, for both wind and solar. Now this red box, what I would like to add here, shows us the German baseload on weekends in summer. And we have an expected peak generation in the year 2020, which is showed by this blue dashed line. And I think from this figure it is clear in the next years we will have a very clear overlap of these figures, which shows us that it is very necessary to store these energies, and buildings are a key element here. Let me summarize that. Healthy buildings of the future are energy efficient and use less fossil energy. I think that's clear. But they cannot be treated any longer as autonomous energy systems due to this volatile nature of the renewable energy. They necessarily need to be able to store electrical and thermal energy to contribute to wind and solar energy utilization. And last but not least, these buildings are network compatible. That means they are able to communicate with the superordinated control of a grid, and they cannot be treated as passive systems any longer. Now, dear colleagues, in order to design, build, and operate such buildings, there's a last thing missing, a very important one. It's the respective integral planning aids, digital planning tools, multi-scale and multi-level performance simulation. This is something we are currently investigating in a very interesting another annex project under the umbrella of the IEA, the Annex 60. Together with my colleague Michael Wetter from the US, I'm the operating agent of that program. We collaborate with, I think it's around 100 scientists. It's 38 institutes from 16 countries where we are currently thinking and developing of the next generation of such computational tools. Of course, one can consider that on a different scale as well, including cost, life cycle cost analysis, and to go to sustainability certification in order to close that picture. Now, in the end, in order to show you the importance of such integrated new tools and the new thinking, the new interdisciplinary thinking, I would like to show you the idea of a new project we currently run in Aachen. It's the NF Campus Roadmap RWTH Aachen project, with the idea to develop a refurbishment strategy from an energy point of view for the entire Aachen campus. Now, this project has been initiated by our colleagues from the E.ON Energy Research Center. With the colleagues, we have a very healthy and truthful collaboration. We are immediate neighbors. And other participants of that project are a Department for Facility Management of the university. And we also have our colleagues from architecture in that project collaborating here. Now, within that project, we necessarily need to generate models for the power and heat generation, models for the distribution network, models of all buildings, and with the respective energy systems. These models are connected to the energy performance monitoring, which is already equipped at the campus, in order to dynamically develop refurbishment scenarios and to optimize them. Having said this, it is clear that you can't use tools from scratch or tools from the market in order to develop such an optimization strategy. In order to model the huge, these huge data, we are using a geographical information system as database. And together with the tools which have been developed in Aachen, the building tools, we have high information level, low information level. We are combining this and translating this information in order to obtain a dynamic energy system model of the entire campus, together with the grid tools. Now, this dynamic model can be used to analyze, to visualize different scenarios, but considering the full picture. And I think with this, it is clear that just considering a single building, putting some insulation to it, is not a true solution. Yeah? It might end up in a local optimum, but not in a global optimum. And therefore, we have to enlarge the picture. Whoa, now I have to try a summary. Yeah? Difficult topic, but I think we all know that buildings have emerged from shelter to net plus energy buildings. At the same time, I think we need to be aware that the whole discipline of building physics, having its origin in, I've worked at such an institute before, in moisture-related problems, then there came the air quality and all these problems. This today is a very interdisciplinary topic and towards creating a healthy and productive environment, but at the same time knowing about all the building physics fundamentals in the background, which are as well important, of course. Simple control devices need to be further advanced in order to communicate with the superordinated control of a grid, for instance, via demand-side management. And at the same time, we need to further advance our models, our existing models, in order to be able to design, build, and operate such systems. We need multi-physics tool in order to do that. As we would like to further develop passive buildings, a passive house is a good marketing instrument, but perhaps not the healthy building of the future, because healthy buildings of the future are for us network-compatible buildings. And this is at least what we, I would say, in Aachen think that healthy building means in terms of energy efficiency, and of course you're cordially invited to follow that idea. Thank you very much.